Hi, everyone. It's Megan Dwyer here. You've probably seen me a couple of times. I've done a few streams lately. I know the stream was just posted, so awesome that you all were able to get here tonight. If you're in New England and you have some trouble with power right now, I'm in the same boat. We've been on and off with power all day, so hopefully we'll be good for this whole hour. We should be good, but this will be recorded, so if somehow you end up getting kicked out because of power, then feel free to watch it later on Fiveable. It'll be up there. Hi, everybody. I see some similar names. It's good to see you guys again. See your names on the list. But the weeks are winding down. We're getting closer, and we're just reviewing some things that we hadn't gone over during the year or things you guys had asked about. So this stream is specifically about L'Hopital's rule. We're going to do a couple free response questions at the end because really free response is what we need to practice right now because that's all the test is. So we'll move forward with that. Feel free to ask me questions, whether it's about something else, I'll do my best to answer it, or if it's about L'Hopital's rule or about the setup of the test, we'll go with it as we go. Okay. Yes, it's getting closer, but you guys will do great. Don't worry. So I'm going to start my presentation. Let me just make that bigger for you guys, and we'll go into L'Hopital's rule. Before that, as we start every stream, there's other dates and other AP classes that we work with. So make sure if you have other AP classes, you tune in these days to see the classes that you might want. And make sure you follow us on all our social media to make sure that you're up to date on the latest, like classes like this, which we literally just posted this maybe last night or this morning. So things can come up at any moment. So it's really good if you can be up to date with it. So this is what we'll do today. First, we'll talk about what is L'Hopital's rule. Hopefully all of you know it, but it's always good to review. We'll talk about how to use L'Hopital's rule, and we'll talk about when to use L'Hopital's rule. And then we'll practice. I have a couple free response questions for us to do tonight. Okay, so what is L'Hopital's rule? L'Hopital's rule is this big long thing that means something really pretty nice. But if you have two differentiable functions, f and g, and they're on an open interval that contains x equaling a, so an x value that we're going to call a, if the limit as, and I guess this should be put first, but the limit as x approaches a of f of x divided by g of x, if both f of x and g of x, their limits as x approaches a, both go to 0 or both go to infinity, then you can take what would have been the limit of f of x over g of x and make it the limit of, if you can't see it there, it's kind of small. It says f prime of x over g prime of x. So the limit of x as it approaching a of the original functions is the same as the limit as x approaches a of the two derivative functions divided by each other, same ratio. And this statement does still work if you're working with a one-sided limit or a limit at infinity. So we'll deal with some of those situations as we go through today. Are there any questions on that rule? Or anything you don't remember that you want to talk about? We're going to go over some common things to watch out for and when to use it. Yes, you can use it more than once. That's a great question. So you can use L'Hopital's rule as many times as it works. You can use it 3 times, 4 times, if hopefully not more than twice. That would be a lot of work for AP to give you, especially when you have other things, they have other things to assess you on. So on an AP test, I wouldn't expect to use it more than twice, but you could. All right. Perla, good question. Is it L'Hopital or L'Hopital? So I've seen it both ways. AP actually does spell it with the S in it. You can spell it however you want. I don't think it matters. Yeah. So I've heard it with an S and without an S. There's lots of memes about how if you use it wrong, you'll go to the hospital and all that. Yes, we're going to look at what this looks like in a free response question because it actually can look kind of cool. Thank you for your laughs. I really appreciate it. Okay, let's take a look at the next slide and let's look at how to use L'Hopital's rule. So I kind of made this out step by step, probably a little bit more than it needed to be, but we'll go through it anyway. So first you need to test your limit and find out if you can use L'Hopital's rule. So there's only a few instances that you can use L'Hopital's rule. The main ones we're looking to use are when it's 0 over 0 and when it's infinity over infinity. So if you have something that's in a different kind of form that maybe is like 1 over 0 or infinity over 2, those are not in our indeterminate forms. Those have different limits. You cannot apply L'Hopital's rule. If you try to use L'Hopital's rule when it can't be applied, then you'll get the wrong answer. Oh, you guys are good. Even with just 8 people in the chat, you guys are cracking me up. So good job. So again, if it does equal 0 over 0 or infinity over infinity, on a free response question, and we'll go through this a couple times, but on a free response question, you need to show that those limits, the numerator and the denominator separately, are each approaching that value. Okay, so just as I stated, let's look back for a second. If you look at how I stated in this, how the limit as f of x, limit as x approaches a of f of x equals 0, and limit as x approaches a of g of x equals 0, you need to state them separately like that in the free response question, or you will not get credit for that part of the question. So it's a really important distinction for the free response question. And we'll look at that again closer as we go. Okay. Okay, then if it works, you find the derivative of each piece, f of x and g of x. So you find f prime and g prime, and you just take the same limit using the derivatives instead of the original functions. And it'll give you the same answer as if it was, as long as it was in one of those indeterminate forms. Now, there are other indeterminate forms that we can use L'Hopital's rule with. But basically, anytime you run into a different type of indeterminate form, you have to turn it into one of these. But the only ones that AP tests you on are these two, 0 over 0 and infinity over infinity. AP will never give you one that's in like 0 times infinity, although you can use this with that. Okay. So, and then going back to your question of, can you use this more than once? If it is still in an indeterminate form, go back to step 1 and repeat. So you can use this as many times as you want. Again, hopefully not too many times. Okay, something to watch out for. Watch out, L'Hopital's rule is not the quotient rule. Okay, so it is a fraction, a rational function, but when you take the derivative of f and g, you're taking them separately, and you're just putting their derivatives one on top of the other back into the rational function. So do not use quotient rule here. This cannot replace quotient rule. Okay, so if you have a fraction, a rational function that you're trying to take the derivative of, you can't just use L'Hopital's rule. You need a limit, and you need a limit that says 0 over 0 or infinity over infinity. So this quotient rule and L'Hopital's rule, very different situations. Do not use quotient rule when you're taking L'Hopital's rule. Okay, don't be that guy. Yes, you can only use L'Hopital's rule when you're in either the form 0 over 0 or infinity over infinity. If you try to use it on something that's not an indeterminate form, okay. All right, when to use L'Hopital's rule. So we've talked about this a little bit already, but it's when it appears in just those two indeterminate forms, 0 over 0 and infinity over infinity. I can't stress that enough. And as I said before, there's some other indeterminate forms, but they're not assessed on the AP exam. Now, there are some times when you can use L'Hopital's rule, but maybe you don't have to. Maybe it'll make it faster, or there are times when it could make it more complicated. So we should look into times where it might make it a little more complicated. The best times to use it and the times where it's going to be most useful are when you're working with trig functions, when you're working with exponential functions. Sometimes when you can just do algebra, it's easier to do algebra, or it'll take less time to do algebra. So that's, if you can use it, sometimes it might make it a little bit harder, and we'll look at some examples that might happen with. That's a good question. So whenever you're thinking about using L'Hopital's rule, the first thing you should always do is plug in the values into the limit to see if it works. Because if it doesn't work right then, you know you can't use it. The times when you might not want to use it, but you can, is when taking the derivative uses a lot of chain rule and might make an even uglier function that would require you to use L'Hopital's rule again. So if you can use algebra, if you can factor and cancel terms out, it's probably better to do that. But we're going to go over one. Radical functions, square root functions, can make using L'Hopital's rule kind of hard, especially when they have a function inside. So that's one that we'll look at in a little bit. Okay, so let's look at these two functions here. Should you use L'Hopital's rule? Let's talk about this first one on the left. The limit as x approaches 2 of x minus 1 over x squared minus 4. What do you guys think? Should you use L'Hopital's rule? Not for the first one. Why not? Okay, this first one here. So let's go over and let's do this limit out just to practice. And it's probably been a while since you've done some limits if you've been practicing. So let's go and look at that. Okay, so we've got our function or our limit here. And the first thing to do is to plug in, oh, sorry, I probably need to make the screen bigger. There we go. Okay, good. Awesome. So first thing to do is plug in 2 and see what happens. So we're going to end up with 2 minus 1 over 2 squared minus 4. Well, this would be 1 over 0. This is not one of our indeterminate forms, okay? So this is not indeterminate form. What is this limit, though? Good. Okay, so this limit does not exist. You could also say it's infinity. Those are actually interchangeable on the AP exam. You can say does not exist or infinity for an indeterminate form. Those are both, or sorry, for this indeterminate form if something was infinity. Yeah, so if you're negative infinity, positive infinity, you could just write does not exist and that would cover that, which is kind of a nice thing. But yes, so since it's not 0 over 0, we cannot use L'Hopital's rule. There's no reason to keep going here. So this is a no L'Hopital's rule. And I'm just going to abbreviate that LH for now just to save some time. Okay. Let's go back. I'm not ready for that one yet. Let me bring you back to my presentation. There actually is no more correct answer, Nikki. It could be does not exist or infinity. Undefined or infinity would both actually work. The only time is if they're asking you to specify positive or negative infinity. That's something you would want to figure out. In this case, it would be positive because the number in the numerator is positive. If it had been negative 1 over 0, we'd be going to negative infinity. Sorry, just switching screens one more time. Not the last time for the night, but okay. So you guys told me no for this one. What about this next one? Perla, that's a good question. I don't know if you will be allowed to see your test since the teachers are getting it, but I assume so. I think your teachers will be allowed to share with you even if College Board doesn't give it back to you. But I'm not sure. Okay, second one. The limit as x approaches infinity of 2 over x plus 1. Awesome. Yeah, Akshita, that's exactly right. So it will be 0. Exactly. Yeah. So if we plug in infinity, we're going to get 2 over infinity plus 1. Infinity plus 1 is still infinity. But we know that if we have infinity in the denominator is getting larger and larger and larger so fast. So your fraction is getting closer and closer and closer to 0. So the limit of this one is actually 0. And there is no L'Hopital's rule involved. It does have a limit going towards infinity, but infinity is only going to be in one spot, just in the denominator. So this is not in our indeterminate form. Okay. Let's try some others. How about this one on the left here? The limit as x approaches -1, x plus 1 over x squared minus 1. Awesome. Yes. Great. So it is 0 over 0. Great job, you guys. So you can use L'Hopital's rule. And this one we're going to look at later. You could use it. Yeah, these problems, L'Hopital's rule make it much easier. You could also do algebra with ones like this. Yes, Perla, exactly. So we'll show it both ways. I'll show you how to do it both ways in a minute. But the one we're going to focus on is, yep, difference of two squares. Exactly. How about this second one here? Can we use L'Hopital's rule? Rashika, there are some instances where, with what you know about limits so far, you can only use L'Hopital's rule. So yes, there are instances where L'Hopital's rule would really be the only thing you know how to do. And this one right here, this is a perfect example of one you definitely want to use L'Hopital's rule for, because you've got a trig function in here, you've got exponential functions in here, but you still have to make sure it's in indeterminate form. Yes, it is. So we are going to get 0 over 0 for this one. And we're going to go practice these now just to make sure we understand what to do. So let's go look at this second one we just talked about here. I'm going to switch back. Okay, let's look at this next one here. Okay, so I'm going to go over, this is not in a free response question, obviously, but I'm going to go over what it would look like to evaluate this free response style, because everything you're going to be doing is free response style on this one. So the first thing I would do in kind of my scratch work is plug in 0 here. So I would say 6e to the 4 times 0, so 0 minus 2e to the 0 minus 4 over sine of 2 times 0, which is just 0. Okay, so this would be 6 minus 2 minus 4, because e to the 0 is just going to be 1. This is just 1 here. Over sine of 0. Well, sine of 0 is 0. Okay, again, your unit values, you should have them memorized as much as you can, especially to save yourself time, which this would then be 0 over 0. Now, you might think that this would be enough to say that you can use L'Hopital's rule, but free response questions say, no, this is not enough. You need to show us a little bit more about the limits individually. So on a free response question, when you're using L'Hopital's rule, you have to do this. The limit as x approaches 0 of the numerator, so 6e to the 4x minus 2e to the 3x minus 4 equals, and then you've done the math out already. AP doesn't really need to see your math, but they need to know that you know that equals 0. You can show the math if you want, but as long as you write equals 0, you don't really have to show the rest of those steps. And then they want to see this. And the limit as x approaches 0 of sine of 2x, that also equals 0. And then you can say something like this. Since the limit as x approaches 0 of 6e to the 4x minus 2e to the 3x minus 4 equals the limit as x approaches 0 of sine of 2x equals 0, we can use L'Hopital's rule. Okay, I'm just going to check the chat. When you're using L'Hopital's rule, you do not have to explain why a function is continuous and differentiable. Is that your question, Nikki? Oh, no, yeah, we do not have to state that, and we don't have to use the continuous and differentiable, not with L'Hopital's rule. You're welcome. Could you send us these slides? So these slides will be up on Fiveable. If you look at this stream, the slides will be a resource, so you can definitely have the slides. Okay. So we can use L'Hopital's rule. So I haven't done it yet. So let's look at how we use L'Hopital's rule here. Okay. So we want to take the derivative of the numerator and the derivative of the denominator separately. That sentence is enough on the right. So this right here, yes, that would be enough to say you can use L'Hopital's rule. Okay, awesome. Let me move this over so you can see it a little better. Okay. So now let's find these derivatives. Do you remember the derivative of e to the 4x? You know what that would be? Four e to the 4x. Awesome. And since we have a coefficient in front, we've got to multiply that 4. So we get 24e to the 4x. Okay, good. Remembering to use chain rule. Minus 6e to the 3x. And then the 4 is going to go away. The derivative of 4 is just 0. And how about the derivative of sine of 2x? What will that be? Two cosine 2x. Awesome. Great job. 2 cosine 2x is right. Great work there. Okay, so now we've got our derivatives. So now this is what we can say. We can say the limit as x approaches 0 of 6e to the 4x minus 2e to the 3x minus 4 over sine of 2x equals the limit as x approaches 0 of 24e to the 4x minus 6e to the 3x over 2 cosine of 2x. Okay, I'm going to give you guys a minute. I'm going to do this math out here, but if you want to look away for a second and try it on your own, I will not talk for a minute. No, this should be a 0, sorry. So Anika, are you talking about when your question about evaluating the limit at both parts? Do you mean, let me go back up. Do you mean this step in the box right here? Yes, you have to show, you will only get credit if you show that these limits are separate. The limit of the numerator separate from the limit of the denominator. You could write, of all the work I've done on the left side here, you could write all of this, and this would be enough to start your problem. And then this is the next thing that I would say you need to write right here. Yeah, so actually you can't just say due to 0 over 0. No, you have to show the limits. Yeah, I know. Takes a little bit more time. Okay, so we evaluate this. We should get, did anyone get an answer yet? 9, awesome. Great job. That's right. Great. And yes, so L'Hopital's rule does appear in word problems, and it actually looks a little bit different than you would expect. They really make sure you're thinking about L'Hopital's rule. So we will go over 2 problems that involve L'Hopital's rule. Is anyone that's with us tonight in BC calculus? Is anyone in BC calculus here? Well, one of the questions I do is from the BC calculus test. And if you are in BC, I'll do it just so people who are in BC can watch it. But it's only one part. AB, you can do the first 3 parts of the free response question. So don't worry too much. It won't take up too much of the presentation. Okay, so we got 9 on this one. Let's look at this next one here. This one right here, this one, we've got to, let me make it a little bigger. Yes, you guys are doing great. Okay. Oh, sorry, this limit, I believe, should be infinity here. I thought I had changed it, but I'm not sure why I didn't. This should be approaches infinity, because I was going to say, otherwise you couldn't use L'Hopital's rule. Yeah. So limit as x approaches infinity of this. Can we use L'Hopital's rule? Yes. Yes. Okay. So let's go through that a little bit. Let's see what that looks like. Okay. So I'm going to try and write kind of what I was telling you guys to write before of what this would look like. So since the limit as x approaches infinity of root x squared plus 1 equals the limit as x approaches infinity of 4x equals infinity, we can use L'Hopital's rule. Correct. So it doesn't matter. This can be anything as long as it makes it 0 over 0 or infinity over infinity in your answer, then you can use L'Hopital's rule. This could be any number here. Okay. Awesome. Okay, so we can use L'Hopital's rule. So we need to take the derivatives. The derivative of the numerator. Don't forget chain rule here. Yes, yes. Okay, so chain rule here is going to be, I'm going to rewrite this because I work better when I'm using exponents. So this is x squared plus 1 to the 1/2. So this is going to be 1/2 x squared plus 1 to the negative 1/2 times 2x. Don't forget chain rule here. So let's clean that up a little bit just so it's a little neater. It's going to be 2x over 2 root x squared plus 1. So we can actually simplify this even more. X over root x squared plus 1. Fun. That one looks good. Okay, let's keep going. So that's the derivative of the numerator. Oh, Akshita already is ahead of us here. So if we go to the bottom and we take the derivative of 4x, we get 4. And so you're like, oh, that looks promising. The bottom is only going to be 4. But that's not really what happened because our numerator turned into another rational function. Okay, so when we go to rewrite this, it's right over here. The limit as x approaches infinity of root x squared plus 1 over 4x equals the limit as x approaches infinity. And the way this will simplify out is it'll be x over 4 times the square root of x squared plus 1. Oh, okay. So we get infinity over infinity again if we're going to do this out. And then what's going to happen when you take the derivative again of the square root of x squared plus 1? It's going to go back to what you had before. And you're going to end up with another kind of ugly derivative, that chain rule again. And it's going to take a while for you to get to what you want. And so this is a case, this one is a case where you can use L'Hopital's rule. But it might not be your best option. But this one is actually a pretty tricky one in general because it requires some rewriting in order for even the algebra to be a little bit better for you. So I would say if you see, so Rashika, if you see a function, let's go back up. If you see a radical function with a function inside it, try something else. Try and use your algebra before you go to L'Hopital's rule. The other option is manipulating it with algebra and making it look a little bit different. Okay, so we're going to go through that algebra step right now. So let's rewrite this. Okay. I know sometimes the algebra you go to, it's like, oh, I get it, but I wouldn't have thought of that. So let me show you something that you should do when you have radicals and you're taking the limits. So one good thing that we can do here is make it so that this whole thing is under a square root. So we want to rewrite the denominator. We want to rewrite this so that it's under the square root. Okay. So we're going to make it look like this. The limit as x approaches infinity of the square root, and let's make this a bigger square root here. The square root, and then on the top it's still x squared plus 1. On the bottom, I'm going to write 16x squared because what I did was I moved it into the square root. Okay, so I said, well, if it was 4x out of a square root, then if I make it 16x squared within the square root, now if I had taken the square root, I would be back where I started. So I can kind of almost undo what I would normally do when a square root was happening. Okay. From here, now I can do a little bit more simplification. Okay, so I'm going to split this into two fractions. So this is the same thing as the limit as x approaches infinity and square root. We could make this x squared over 16x squared plus 1 over 16x squared. Okay, good with that? Make sure you're asking questions in the chat if you have them. Okay, we can simplify this. So let's simplify even more. That's an infinity. The x squareds can cancel out. So we end up with the square root of 1 over 16 plus 1 over 16x squared. Okay. Rational functions are continuous. Square roots are continuous, which means you can move the limit inside the square root and apply the limit to what's inside the square root. Just like that. Okay. So now we need to apply the limit to each of these things. It might have been a while since you do this, but when you want the limit as something's approaching infinity of a constant, it just stays a constant. So the limit as x approaches infinity of 1 over 16 is just 1 over 16. The limit as x approaches infinity of 1 over 16x squared, we'll plug infinity in for x, and we'll get 1 over infinity. This will give us 1 over infinity, which will be 0. 1 over 16, square root of 1 over 16 plus 0 is just 1 over 16 square rooted. So we get 1 over 4 is our final answer. Yes, great. 1 over 4 is exactly right. Limit as x approaches infinity of the square root of x squared plus 1 over 4x is 1 over 4. Rashika, you probably could do it with rationalizing the numerator. Yeah. I'm not sure what that would look like or if that would take longer, but you could definitely. Yeah, this is a really complicated one. This seems like it would be a really good multiple choice question. I don't know if they would give you a L'Hopital's rule problem like this when it's something like when you only have 2 free response questions. They're really looking to make sure they're assessing your calculus skills as opposed to your algebra skills. But now you're ready for one like this. If you see a square root, get everything under the square root or rationalize it. But I agree. I don't think you're going to be seeing something like this. Would any chain rule with x inside need to use something else because the x would always stay? Not necessarily, because sometimes when it switches sides if with the numerator denominator, it might be okay. Or one side of the numerator denominator becomes a constant and then it's okay. So no, sometimes you can use, even if you need chain rule with x, you can use L'Hopital's rule. Okay. I'm just going to look at the presentation for a second, see if I need to go back to that or if I can just go right on. Okay, so we're going to move on to the free response questions now and show you how to use it in a free response. We'll go through all the parts because we have time and it's good to practice a free response in total. And I've got 2 questions. Hopefully we'll get through both, but we'll start with the first one. This first one we're doing is from last year's test. It is the last question on last year's test. So we're going to practice it. It's a really good one, and it actually applies to what we talked about last week with, oh, actually, I don't know if we got to the squeeze theorem last week. I think we ran out of time. We didn't get to squeeze it in, as the joke I made last time. But we will talk about it tonight because we can use the squeeze theorem tonight. We'll use L'Hopital's rule. That's a good one, Akshita. Thank you. But yeah, you guys are doing great. So we'll do this one. We'll see how this goes, and we'll move on from there. All right. This is really kind of turning into a class. You guys keep coming back every week, and it's awesome. I recognize your names every time. Okay. So we've got f, g, and h, and all of these functions are twice differentiable. That's great. And we know that g of 2 equals h of 2 equals 4. So we know that g of 2 and h of 2 are both 4, which is also good. And we know that we've got this tangent line here, and that line is tangent to both graphs at 2, which is good. That gives us a lot of information that we'll talk about later. And yeah, it's at 2 for both of them. Okay. Part A, find h prime of 2. Any suggestions for h prime of 2? I'm going to let you guys think about this. Good. Yes, Rishika, you are exactly right. How did you know it was 2/3? Awesome. Exactly. So yeah, so this right here, it says this line is tangent to them at 2. If that line is tangent to them, then this is our slope. This is our slope. So our answer for this one is very simple. H prime of 2 equals 2/3. Great. Tangent line practice. We got it down. Doing good. So, okay, question mark. So h prime of 2. So we know that this line here, sorry, let me erase the marks I did. Oh, I didn't know it would erase the problem. So I can't erase that. This line here, this line is tangent to h at 2. So if it's tangent to h at 2, that means it shares its slope at 2. So this function has a slope of 2/3. And so that's got to be what h prime will be at 2 because its slope, this is also at 2 and it has the same slope. So we just got it from the function. Okay. So part B, let a be the function given by that nice thing. Write an expression for a prime of x and find a prime of 2. Okay, so we've got some derivative practice here. What rules do we need to use here? Product rule, awesome. So we've got 3x cubed times h of x. So a prime. Let's just bring this 3 out front and do the rest of the work in here. So first times the derivative of the second plus the second times the derivative of the first. So 3x squared times h of x. Okay, and then we can distribute this 3a prime of x is 3x cubed h prime of x plus 9x squared h of x. Okay, and if it's a prime of 2, then we just want to plug 2 in here. So we get 3 times 2 cubed, which is 8, h prime of 2, 9 times 2 squared, which is 4, h of 2. Okay, we've got, let's see, h prime of 2. Do we know h prime of 2? Yes, we got it over here. 3 times 8 times 2/3 plus 9 times 4 times h of 2. H of 2 is 4. And yes, you got it. It is 160. So when we multiply all these together and add them up, we are going to get 160. 24 times 2/3 is going to be, 24 divided by 3 is going to give us 8 times 2. This is just 16 here. And 9 times 4 times 4 is going to get us 146. Yes. Yes, absolutely. You could leave it. You could leave it here. Great point. AP does encourage you to leave it here. Yeah, it's nice to leave it unsimplified. Here, let me see why this is in the way of you guys. Maybe I can get this out of the way. Here we go. Okay. It is nice that they're leaving it unsimplified. And yeah, that means that you can stop yourself from maybe making an algebra error. Again, AP is not assessing your algebra. 144, thank you, not 146. I appreciate that. So here, the important thing though is that this step here I don't believe is enough. I think you need to take it one more step. Nikki, that's a good question. So if you simplify, you do not have a higher chance of getting a 5. AP actually thinks that might make it harder because they're afraid, kind of like what I just did and wrote 146 there instead of 144. They're afraid that you're going to make an algebra error. So you get no extra credit or anything for simplifying. Leaving it right here is just as good of an answer. The only time you need to simplify is when you end up needing to use it for the next part. Akshita, I mean, if you have time to do it, go ahead and do that simple math. That's awesome. I also like the simple math. All right, let's talk about part C. Now we're getting into L'Hopital's rule. So we've got this function h of x, and it's got another function inside of it. So we've got x squared minus 4 over 1 minus f of x cubed. And this is for x does not equal 2. It is known, it's known. So this is how they're getting L'Hopital's rule in there. It's known that the limit as x approaches 2 of h of x can be evaluated using L'Hopital's rule. So they're telling you you can use L'Hopital's rule. They're not telling you that you have to test it and see. They're saying this can use L'Hopital's rule. So use the limit as x approaches 2 of h of x to find f of 2 and f prime of 2. Okay, so this is important. We're using h of x to find f of 2 and f prime of 2. All right. Let's focus on this L'Hopital's rule part. This is what we've been waiting for all night. So we've got L'Hopital's rule. It says we can use it, and it says that it wants us to use it, this limit, to find f of 2 and f prime of 2. Okay, so let's start with f of 2. And it's let's write this out. So we've got the limit as x approaches 2 of h of x, and it tells us this is h of x squared minus 4 over 1 minus f of x cubed. How does knowing we can use L'Hopital's rule help us find f of 2 in this case? Take your time. I can wait. Good. Or infinity over infinity. But if one of them is 0, the other must be 0. Exactly. Good. So this means there's only two indeterminate forms you can use, 0 over 0 or infinity over infinity. Well, if you plug this limit into the top, you're going to get 0. Okay, so that means since you can use L'Hopital's rule, that means the limit as x approaches 2 of 1 minus f of x cubed has to also equal 0. Okay, yes, exactly. So in this case, 1 minus f of x cubed has to be 0, which means that, let's get this to the other side, f of x cubed. Well, when we've got 1 on one side, it's not really going to do anything to do all this math out, but just so we can see, f of x is going to have to be 1. And that's at 2 because this is the limit as it's approaching 2. So f of 2, let's go back here, f of 2 equals 1. And that's because we knew we could use L'Hopital's rule. How can we use this again to help us find f prime of 2? Derivatives, yeah, we're going to have to use L'Hopital's rule again because L'Hopital's rule allows us to use it again and use derivatives. So because we know we can apply L'Hopital's rule, we know that this limit, the limit as x approaches 2 of x squared minus 4 over 1 minus f of x cubed is going to be equal to the limit as x approaches 2 of, now we got to take the derivatives of each of these, 2x over negative 3 times f of x squared times, don't forget chain rule, f prime of x. That's the only way we'd be able to do this function. Awesome. Okay, so now we've got this. Yes, exactly. Okay, so we've got this limit here, and we can plug in 2. So we know that this is 2 times 2 over negative 3, f of 2 squared times f prime of 2. And this is what we're going to be solving for here. And we know that this equals 4. Because just as Rashika said, we know that h of 2 is 4, and this is h of x. So we know that this equals 4. Here, let's go back to the top. So they told us here, g of 2 equals h of 2 equals 4. If this is twice differentiable, okay, that means this is continuous. So if we're using this limit as x approaches 2 of h of x. Well, the limit as x approaches 2 of h of x is h of 2, which we already know is 4. Right, exactly. So that's the exact limit we're finding down here. So we can plug in what we know and solve. So we end up with 4 over, well, we know that f of 2 is just 1. So 4 over negative 3 times f prime of 2 equals 4. Again, let's go for the algebra. Negative 4 thirds equals 4 times f prime of 2. And if we divide out that 4, it's going to cancel with the 4 up here, and we're going to get negative 1/3 equals f prime of 2. Perla, I agree. Questions are always welcome and wanted. So ask as many questions as you want, everybody. Does that make sense? Negative 1/3. Thank you, Anika. Awesome. So did you expect them to ask you to use L'Hopital's rule in that way? Probably not, but they found a way to kind of make you need to apply L'Hopital's rule in a way that you haven't had to in the past. Okay. Any more questions on this part? Because this was the big part of this lesson, the L'Hopital's rule part. Awesome. Okay. Okay. The procedure for solving it. Sure. So let's go back. So they told us that this was h of x. They said this was h of x. And they said use the limit of this and the fact that you can apply L'Hopital's rule to find f of 2 and f prime of 2. Okay. So we know we can apply L'Hopital's rule. So we know that it has to be in one of these forms. Has to be in one of these. Well, with the information they gave us, we can plug 2 into our numerator. We can plug 2 in here. And when we plug 2 in, we get 2 squared minus 4, which is 4 minus 4, which is 0. Okay. But because we know we can apply L'Hopital's rule, we know that if the numerator was 0, the denominator also has to be 0. So this 1 minus f of x to the cubed also has to be 0. So we can assume this is true, and we can solve for f of x, which is going to be f of 2 because of the limit. When we do that, we get this over here. Let me redo this over here. F of 2 cubed equals 0. So when we plug in the limit, we're going to get 1 minus f of 2 cubed, which has to equal 0. We add f of 2 cubed to both sides. 1 equals f of 2 cubed. And then if it's just 1, then it's going to be f of 2 is 1. Okay, so we've got the first part. We've got f of 2, but it says also f prime of 2. Now, the only way to find f prime of 2, well, the only thing we know is that we can use L'Hopital's rule. Well, L'Hopital's rule involves finding a derivative, so we know that we can use L'Hopital's rule to get something that has f prime in it. So let's look down here. We apply L'Hopital's rule. So from this step to this step, we've actually plugged in L'Hopital's rule, and yes, exactly. So we've plugged in L'Hopital's rule. We've taken the derivative of the numerator and the derivative of the denominator. The derivative of the denominator is what allowed us to have f prime in our problem, which is going to help us find f prime of 2. We plug in 2. When we plug in 2, we get 2 times 2 on the top over this nice fun thing on the bottom with f of x and f prime of x. And the only way we can go anywhere from here is, well, do we know what this has to be equal to? Because we weren't told that we can apply L'Hopital's rule another time. So how do we know where to go? Well, we do know that this limit as x approaches 2 of h of x that we started with, we know that it's going to equal 4 because they told us at the beginning that h of 2 is 4. Okay, and then something helpful to remember from the beginning, if something's continuous, which we know this function is, then this limit has to equal this value. That's the rule for something being continuous. So we know that this has to be 4 because they told us this. Since we could apply L'Hopital's rule, that means if we take the derivative of both, that answer is still going to be 4. That answer is still going to be 4 over here. So we can plug in everything we know because we know everything besides f prime of 2. So we plug in 2, we plug in f of 2, we plug in 4, and then we solve for f prime of 2. Awesome. Glad to help. Okay. So let's look at this last part here of this question. This applies the squeeze theorem. So this is a pretty good thing to go over. Last year was the first test on AB that they used the squeeze theorem. And so teachers were kind of surprised. But we teach it. It's no worries. And this is really the only way that it's applied. So it's not too bad. But it tells us a couple of things. We know that g of x is less than or equal to h of x. And we're between 1 and 3. And then it says, let k be a function satisfying that it's between g and h. So this right here, this is a telltale sign of you're going to have to use the squeeze theorem. Okay, if you see 3 functions that are separated by inequalities that have the equals underneath, you're going to be using the squeeze theorem most likely. And it wants to know, is k continuous at x equals 2? Okay, so the only explanation you need here is k continuous at x equals 2 is this. Yes, it is. Do you know why? You want to explain why? Let's talk about it. Yes, the squeeze theorem. Yeah, that's a good answer. Okay, so we know that the limit as x approaches 2 of g of x equals the limit as x approaches 2 of h of x equals 4. Okay. Okay, I can scroll back to the question. So here, let me just give you a summary of what it says. It says g of x is less than or equal to k of x is less than or equal to h of x. Okay, it tells us that, and it says, is k continuous at x equals 2? Okay, yeah, we'll talk about the squeeze theorem as we go here. But the squeeze theorem basically says that if you have a function here, k of x, and it's between g of x and h of x, if you want to know the limit as, let's say, actually, let's start with this. If you have the limit as x approaches some number of g of x, and that equals the limit as x approaches that same number of h of x. Sorry, wrote that in the wrong spot. And so let's say those both equal L. Yeah, so these both equal L at this point. Well, if this is L and this is L, then what does k of x have to be? Well, it has to be L. So the limit as x approaches 2, or A in this case, of k of x also has to be L because it's stuck between these two. There's nowhere it can go, and these are the same. So that's what's going to really help us here. So to show something's continuous, k of 2 has to exist. Okay. The limit as x approaches 2 of k of x has to exist. And these two values have to be equal. So this is a review of what makes something continuous at a point. You have to make these three things happen. And because of the squeeze theorem, because of this right here, because we know the limit of g of x and the limit of h of x as they're approaching 2 both equal 4, and we know g of 2 equals 4 and h of 2 equals 4, then we can say by the squeeze theorem, since k, sorry, I'm just writing whatever letters I want now. Since g of x is less than or equal to k of x is less than or equal to h of x, then the limit as x approaches 2 of k of x has to equal 4. And k of 2 also has to be 4. And since they're equal, or since they're exactly the same, so k of 2 equals the limit as x approaches 2 of k of x. K is continuous. So therefore, k is continuous at x equals 2. Yeah, I'll go over that one more time. Let me just go back and make sure I read these. Yeah, okay. So the squeeze theorem in general. Are we good on what the squeeze theorem is in general? Can you guys hear me? Okay, it might just be Nikki. I'll just tell her it's recorded. The squeeze theorem doesn't necessarily mean they're the same function, but it means they're the same value. So that's a good question, Callie. So g of x, h of x, and k of x can all be different functions. Sorry, that should be k. So they can all be different functions, but it just has to be that they all basically have the same value at this one point. So the squeeze theorem does not help you. The squeeze theorem only helps you if these are the same. If these are the same, then K has to be L. Okay. So the only way the squeeze theorem works is if you can tell that g of x and h of x are the same. Well, something that's in between them also has to be the same because it has to be in between the same thing. Okay, make some sense there? K of x has to be L because if it's greater than or equal to g of x and less than or equal to h of x, then it has to be the value in between. So, okay, let me use a number example. If I told you that 2 was less than or equal to h, or let's just do k of 5, was less than or equal to 2. If I told you 2 was less than or equal to k of 5 or less than or equal to 2, then k of 5 would have to be what? What's the only possibility? Okay, yeah, 2, exactly. So that's what the squeeze theorem is saying is if I get the same values on the left of right of this function, then it has to be what's in the middle. Okay, so that's the squeeze theorem. That's all it's saying. When we go back to our problem, we know we were told that g of 2 was 4 and that h of 2 was 4, and we were told it was differentiable, which means they're both continuous. Okay, yeah, exactly. And so if they're both continuous, that means that the limit as x approaches 2 of g of x is going to have to be 4 because continuity tells us that the point has to equal the limit, and that the limit as x approaches 2 of h of x also has to be 4. So we know all this information about g and h, and we know that g of x is less than or equal to k of x is less than or equal to h of x. It needs, for this one, it needs to be continuous. For it asked us, is k continuous? So it asks us if k is continuous at x equals 2. So if g of x is less than or equal to k of x is less than or equal to h of x, then remember for continuity, there's a few things we have to show. We have to find k of 2. And we have to find the limit as x approaches 2 of k of x. And then we have to know that they're equal. Right, exactly. Exactly. If it had a discontinuity, it may not work. So to show continuity, there were 3 things we have to prove. We have to find this value and say that it exists, k of 2. We have to find this value and say it exists. And then we have to show that those 2 values are equal to each other. So do we know what k of 2 is? 4, exactly. So we know it's 4 because of the squeeze theorem. Because of this, k of 2 has to be 4. No, the only reason we need to use, so Rashika just asked, do we need to prove continuity every time we use the squeeze theorem? No, only in this case because the question was, is k continuous? Sometimes it'll just say, what is k of 2? If it says what k of 2 is, you don't have to use continuity. You can just say by the squeeze theorem, k of 2 is 4. But in this case, since it said is k continuous, we need to show that the functions it squeezed between are continuous. So, and do we know the limit as x approaches 2 of k of x? Well, we know these 2 limits. So by the squeeze theorem, this also has to be 4. Great. 4 equals 4. So yes, k is continuous at x equals 2. And we can, all of this middle part here is by the squeeze theorem. We wouldn't have known any of this information without the squeeze theorem. So the squeeze theorem is the only reason we know that both of these are 4. Basically, this statement right here tells us the squeeze theorem. It tells us that K is between two things that are both 4. So by the squeeze theorem, if K is between two things that are 4, K is also 4. It seems a little self-explanatory, but basically you don't have to say because it's between these things, it's 4. You can just say by the squeeze theorem, K is 4, instead of having to explain every time. All right. Okay. Any more questions? Yes. Perla, that's a good question. I think you should get full credit. I think that would probably be up to AP. But I would say anytime you see this here, this like one function less than or equal to another, less than or equal to another, I would just state the squeeze theorem. Like you're going to use the squeeze theorem if you see this here. Yeah, so Akshita, what you said about what the squeeze theorem is, it's basically just saying that we know the limits and the values of the two outer functions, and they're exactly the same. So if this function is in between them, then you're done. Then you've got it. Yeah, I mean, Perla, I would do your best to explain it. If you remember it, then great. I think of squeeze because it's like you're stuck between these two, and there's really no space between them. They're squeezed together. So that's how I remember the name of this one. It's the inequality with 3 functions. And it's when you know things and you know information about the outer functions. And you're looking for the inner function. Okay. You can just write squeeze theorem, Caitlin. All you have to do is write it. So you know you have to use the squeeze theorem. If it's talking about 3 functions, it says one's in between. It tells you about the outside ones, and it asks you something about the inside one. That's really all of that together is a squeeze theorem problem. Okay. And another thing about the squeeze theorem is it really only helps you if g of x and h of x are the same. So like if we had a problem and it said g of x is less than or equal to k of x is less than or equal to h of x, and you were told that g of x was 3 and h of x was 5, you cannot use the squeeze theorem here. And that's because you don't know enough information. So Anika, what do you mean by the last part? Like this part I just did here or before that? Okay, I'm going to keep going with this part. Let me know if I answer your question. So, why it is continuous. So, okay, let me finish explaining this, and then I'll go over continuity one more time, and then we're going to have to shut down for the night. So let's just, only situations where you can use the squeeze theorem is only when g of x and h of x are exactly the same. If you were given something like this and asked about k, you couldn't say anything about it because there's a lot of numbers between 3 and 5. You can't just say 4. We don't know if it's an equal distance between g and h. So in this case, you don't have enough information. So just a tip. They might say, can you use the squeeze theorem in this case? In this case, the answer is no. Okay. I'm going to go over the rule for how to make something continuous one more time, and then I'm going to sign off for the night. So for continuity, Perla, thank you. You've been great. Have a good night. So continuity of a function f at a point C. All right. Bye, Rashika. Bye, Akshita. Okay. Let's finish off here. I want to say bye to you all, but I've got to do this here. Okay. So there's three things you have to prove in this case to prove something's continuous. You have to show that f of c exists. You have to show that the limit as x approaches c of f of x, that also exists. So that means it's the same from both sides. Same limit from left and right. And you have to show that this limit that you got is equal to f of c. Yes, exactly. Okay. So then if all these things are true, if all are true, f of x is continuous at c. So in our question, it said right away, it said, is k continuous at x equals 2? Okay, so as soon as I see is k continuous, I'm going to all of these steps, and I'm using all three of those. So I'm saying I've got to show f of c exists, I've got to show this limit also exists, and I have to show they're equal. Now, by the squeeze theorem, since the two functions on the outside were both continuous and both equal to 4, that's also what k had to be. And so since this was 4 and this was 4, that meant they were equal. Then it was continuous. Exactly. All right. Okay, I hope that helped, that last explanation of why it's continuous. If you want more on why it's continuous, there are other videos on limits and continuity from Unit 1 that are already on Fiveable. Feel free to go watch those. And I hope it helped. You guys were great again tonight. Thank you so much. If you have any questions, feel free to ask or leave them in the chat. But we'll be back again on Monday, so feel free to come back and join us again. Thanks, you guys. Have a great night.